Namaste everyone, this is Dr. Ayesha Butalia. I welcome you all for today's session on the calculating dependency of an attribute, especially using rough set theory. This is a continuation of our previous lectures where we had tried to identify uh, what are the various components of the rough set, that is information system, consists of number of objects, number of attributes, the domain values of each attributes, and the decision function of that table or the problem statement on which the information system has been designed. Next, we discussed about the example and the issues of decision table, how to calculate the indissolubility relation, okay, where we calculated the A basic knowledge sets. These are the preliminary sets, or you can call it as the smallest discernible group of objects, which we call it as equivalent classes. Okay, so these are the related sets, equivalent classes for similar clusters, which is denoted by capital X. Then we saw how to calculate the equivalent classes using this car example of condition attributes, engine size and color on the attribute engine, and to calculate the different approximation set, lower approximation, that is positive region, then boundary region, negative region, upper approximation. And with an example, we try to quote the different regions and the objects related to the different regions. Then later we discussed about the dispensable and indispensable attributes. What is the importance of them? Ultimately, we want to reduce the attributes. Okay, we want to keep only those attributes that preserve the indisciplinary relation and consequently the set approximation. Okay, indisciplinacy is basically the things where there is ambiguity. And we already discussed that rough set theory and the methods. These are applied as a component of hybrid solutions in machine learning and data mining, especially for handling the uncertainty in the data. Rough set theory has been used particularly for rule induction and feature selection. So feature selection basically is feature reduction or maybe data set reduction, where the semantics preservation dimensionality reduction is one of the technique, which when you will find a couple of papers on the similar methods. So rough set theory based data analysis methods have been successfully applied in bioinformatics, economics and finance, medicine, multimedia, web and text mining, signal and image processing, software engineering, robotics and engineering, power systems and control engineering. Because in all these regions, you will find soft computing where you cannot have the precision in the data, accuracy cannot be 100%, you need to have approximation outcomes. And basically, everywhere there is uncertainty in today's real world data dimension. So recently, three regions of rough sets are interpreted as regions of acceptance, rejection, and deferment. So this leads to three-way decision-making approach with the model, which can potentially lead to interesting future applications. But the main part is that before you go to making the uh, decision algorithms on your information systems, you first need to have uh, confined data sets. That means you try to reduce the data sets and remove the redundancy in your data, and for which even normalization is very much popular, which extends to the evaluation, that you reduce the redundancy but still maintaining the consistency. So redux is a word which is used for preserving the uh, indispensable attributes in rough set theory. Okay, so these are usually several such subsets. There can be, n number of such subsets of attributes, and those which are minimal, they are called reducts. So as in our previous lecture, we said that there may be in mushroom plant, we calculated from 16 attributes to 3 attributes, but actually there were n number of reducts, one with 3 attributes, one with 4, and one with 5. So obviously you will try to match with the reduct which has minimal number of attributes. If there are 16 attributes, there can be actually 2 to the power 16 minus 1 combinations. Okay, so they all are actually reducts. But the reduct is where you can make the decision only on the attribute sets. So obviously you will try to reach out the one which is having the minimum number of attributes. Now, what is a core? Core, we discussed earlier that, to calculate a core, we first need to calculate the positive region. Okay, and what is a positive region? So a positive region of B. Okay, what is that? POS, A of P, that is positive region, a positive region of P, that is union of all the lower approximations on every attribute. Okay, so for example, in our, and that too depending upon B star. Okay, you have to include every attribute which belongs to B star. And what is B star? B star is the total number of objects divided by the indissolubility relations on the B. Okay, so as highlighted earlier, if we are saying a positive region of B, you have to calculate the lower approximations of each attribute, okay, on A, and you need to calculate the indissolubility relation on B. You can just have a look on our previous lectures to understand what is indissolubility relation, what is B star. Okay, so ultimately, when this condition is satisfied, then we say that that particular attribute A, okay, is dispensable. You can remove it. But if this is not equal to, okay, then we say that that attribute, if you remove, then the consistency is not maintained. That is why it is not equal to. Okay, so this we have discussed in our previous lecture. So going ahead, if this is not equal to, that means this A is a indispensable. That means it's a very important attribute. It's dispensable means not important, redundant, but indispensable is important. So you need to add this A in the core. Okay, so similarly, you try to catch out each attribute in the attribute set, right? And you calculate the positive region of A, and then you try to find out whether this condition is satisfied. If this is not equal to, then you add it in the core. So this you get, this is how you get the set of the core. So basically, what is the set of the core? It is the set of all the indispensable attributes. Obviously, if each member you are adding, okay, which is indispensable, the set is going to be directly indispensable. So all reducts of A are denoted by RED, that is family of A, that is there can be many minimal sets. The intersection of all reducts of A is a core of A. So you can use this method, one method to calculate A, but another method is that you calculate the reducts and then just do the intersection of all the members of the reducts, and that intersection will nothing, the set of members of that intersection will be nothing but the core. So we had seen the example also. On basis of the condition attributes, headache, pain, temperature, we decide whether the patient has flu or not. Okay, so we had two design reducts. Of course, you can have, see, this is about muscle pain and temperature. So we had taken these two attributes, conditional attributes, and decided the reduct one. Then we took two attributes, headache and temperature, and we can have another reduct. See, we can also have, headache and muscle pain also as reduct 3. Clear? And we can have reduct 4 where we can have all the 3 conditional attributes as well. Even reduct can be only headache. Even reduct can be only muscle pain. Even reduct can be only temperature. But since we immediately by looking at the data set, we can see that if you take only the reduct of headache, somewhere it is yes and somewhere it is no. So obviously it is this is not going, cannot be individual attribute that can be a decision maker, whether only the headache cannot be a decision maker whether you have a flu or not. Similarly, if we only take reduct as muscle pain, somewhere it is yes and somewhere it is no. So again, Just by taking muscle pain, you cannot say that it is, because see, if this is yes here, this is no here. If this is no here, still it is no here. Hence, we say that only headache cannot be a reduct. Now, if you say it is yes here, but it is no here. Similarly, it is no here, but it is no here. So this is again an ambiguity, right? So this cannot be a reduct. This cannot be a decision maker factor. Similarly, if you say temperature, this is normal here, so it is no. Now, again, it's a normal here, it is no. So temperature alone can be a decision factor for flu, yes or no. But still, only normal is not the case. You have to see all the domain values of temperature. So let's see another domain value that is high. So here, if you can see, there is a high temperature, the flu is yes. But over here, there is a high temperature, but the flu is no. So again, you can say that only temperature cannot be the decision factor, right? So hence it cannot be a reduct. So similarly, you have to have the permutation combination of each and every one. Since the data set is small, it is very easy for us to, identify the reducts without even any mathematical calculations. But generally, when you are opting for machine learning or data mining algorithms, the more the data set is large, the more your accuracy level of deciding the algorithm, okay, or defining the algorithm, or to assign the model, to analyze the model, to design the model, to decide whether it's a descriptive or predictive model. All these issues could be more accurate if the data set is large. So obviously, when the data set is large, you need to have certain algorithm to even decide the reducts. Okay, so for that, preliminary approach is that you find out the disability matrix. So in our previous lecture, we saw how to calculate the member of the decision or the disability matrix. Okay, and then we also saw how to calculate the disability function. Please go through our previous lecture to understand this. So now, if suppose this is an example where you have U1, U2, U3, U4 as the set of U, that is objects, then you have A, B, C as the condition attributes, D as the decision attribute. Okay, so we calculate the decision matrix like this. U1, U2, U3, you discard the fourth last one, and here you discard the first one, U2, U3, U4. Then you see about U1 and U2 combination. So if you see here U1 and U2, A0, A1, it's not same, B1 is same, C1, 0 again is not same. So what is not same? A and C. So you mention here A and C, right? Whenever you put gamma means all the attributes are not same. Clear? So this is how you create the disability matrix. Then you use the disability function where what you do is you take each, this may sound a bit mathematical and complex, but by seeing this example, it will be very more clear. You take each value of that disability matrix and put it here. Okay, now this comma is here, you replace it by AND operator. And then next, again you write B and there is gamma or C, then you put it AND operator. And this in between, you put the OR operator. So similarly, you find out your disability function. And then using the axiom rules, okay, of normalization, you can go through that presentation and then you reduce it to the minimal set. So here after this evaluation, it is B and C. So again, this is comma here. So B comma C would be the reduct. How this B and C has come, this evaluation has been given using the axiom rules. So there's another example. Same, you can evaluate using the disability function and the axiom rules to the minimal reduct. Okay, now in this particular example, after doing all the analysis, you get two reducts, reduct 1 and reduct 2, right? Because ultimately, see here, it was the intersection operator. Okay, but if there is an AND operator coming at the last, then AND operator means the left hand side and right hand side, there will be two reducts. Okay, if there are three attributes here and all the three attributes as an AND operator, then after this evaluation, there will be three reducts. Looking at this example, see this is the intersection operator, this is the intersection operator, right? So C2 and C1, this is one reduct, okay, and this is another reduct. So C1, C2 is another reduct. Here there is an AND operator, okay, so C1 is another reduct, C2 is another reduct. So after seeing this, you can visualize that there are three reducts out of this disability matrix. Similarly, in this case, when it was evaluated, okay, the explanation is given as per year. See, there are, in the end, you got this as final. So this is an intersection. So obviously B and C is a single reduct. B and D is it a single, this is a single reduct, but there is an and operator here. That means this is one reduct and this is one reduct. This cannot be combined as a single reduct. So there are two reducts over here, B comma C and B comma D. Okay, so when you do the intersection of these two reducts, okay, you get B. So B will be nothing but the core. That means B is a totally indispensable attribute. Okay, in whatever problem statement you have, depending upon this particular data set, B will be a compulsory attribute. Okay, for example, you have ICICI customers. Okay, so you have got n number of attributes and lakhs of rows. Now today we are just concentrating on the people who have FDs. Okay, so fixed deposits. So obviously your attribute combination reduct will be totally only on the FDs, so the reduct would be less. So if there are say 25 attributes dominating the customer, for FDs only 5 attributes or maybe even 2 attributes would be sufficient to identify whether this person is having FD or not. So it, now the problem statement is FD. Okay, so reduct will be something else. Now other people, those who are having some mutual funds related with ICICI. So obviously some another attributes will try to dominate to identify who are the customers. So the reduct for that problem statement would be different. Okay, so the data set is same, but the problem statement is different. The dimensionality is different. The feature selection is different. So the moment feature selection is different, the reducts would be different. But from the core, you can understand that your core is the very, very important attribute. And in a database design, gradually you will understand that a core can also be the primary key of that particular relation. If as a DBA you are working and you have got a large data set and you have to decide the functional dependency. So on the left hand side, along with the primary key, there can be other candidate keys. So core will be helpful to you to decide the primary key, candidate key, super key, and so on. Okay. So going on with the dependency of the attribute, why it is so important? Because as said earlier, whether it is artificial intelligence, machine learning, data mining, whenever it comes to soft computing, pattern recognition, pattern mining, pattern extraction becomes the main part. The moment you extract the pattern, then it goes further. So to identify the patterns, first you have to identify the dependency. Okay, because whenever there is dependency, there only you can identify the patterns. And if there are a lot of functional dependencies, then the pattern mining becomes complex. So we try to go step by step, right? So in normalization also, from 1NF to 2NF to 3NF, we try to identify functional dependencies and then try to convert it into F, F plus, cardinal sets, and so on. You can again go through the normalization topic on our YouTube channel for those type of information. So basically, for calculating the dependency, first of all, why to calculate the dependency? Because the moment we understand that it is dependent, that means it is a indispensable attribute. Now, how much it is dependent will categorize how much indispensable it is. Okay, and these all can be understood by the functional dependencies. And the moment you identify the functional dependencies, pattern extraction becomes easier. The moment you identify the patterns, then it becomes easier for you to write the algorithms for your problem statements. So coming to the next, dependency of an attribute. So dependency of an attribute gamma, A of B, okay, it is equal to cardinality of positive region A of B divided by cardinality of the entire set U. Okay, that means total number of objects. Now, first we will see the positive region A of D. D is the decision attribute here, okay, where B can be anything, even it can be a conditional attribute or a set of conditional attributes or maybe decision attribute. So you try to calculate all the lower approximations on each of the equivalence classes. Okay, so every equivalence class should be a member of B star, and B star is should be member of the entire, that means indissolubility relation. That means it should be the subset of the all the conditional attributes equivalence classes. Okay, this also we had done with example in our previous lectures. So if A tends to B means B is dependent on A. So A tends to B on K. That means 0 is less than or equal to K is less than or equal to 1. If K is equal to gamma A of B. So in simple terms, K is nothing but the dependency. Okay. So if B is dependent to degree K on the set A in S, if K is equal to 1, then B is totally dependent on A. So that means it is a indispensable attribute. If K is equal to 0, then B is totally independent of A. That means, there is no dependency. So no pattern can be found out on this type of functional dependency. Okay. Else means if it is between 0 to 1, B is roughly dependent on A. Okay, in our previous examples, in the previous lectures, we saw that there was a lower approximation on propane. Okay, so propane where the decision of the car was good, right? So that was a positive region, correct? So even lower approximation is nothing but the positive region, but you have to calculate lower approximation on all the attributes, right? Now, in previous example, we had only considered engine, but if you consider the lower approximation on engine, color, size, or the combination of all the permutation combinations, then it becomes positive region, right? So there was 0 means 1 means it was the car was good when it was propane. Then there was something known as the negative region where when the engine was diesel, then it was totally bad. When there was gasoline, when it was a condition of maybe. That means uh, sometimes the gasoline engine was good, sometimes it was bad, and the parameters which was deciding it was the size and the color associated with the engine. Okay, so that means gasoline was between 0 and 1, and that's why it was roughly dependent. We had uh, conceptualized at that time that if the it is a crisp set, that means whether you can say it is 0 or 1. Okay, whether the car is definitely good or bad on certain characteristics, then this is a crisp set, right? One can give you a crisp set of good cars and of conditions, and another of bad, right? But if there is a maybe type of clause, then that is called as a rough set. So same we are trying to identify here with the help of algorithms. If k is equal to 1, that is dependency is total. 1 means total because the value of k is between 0 and 1 only. So 1 is the highest. So if it is highest, then it is totally dependent. If it is 0, it is totally independent. And if it is in between, that it is rough. That means it is a maybe type of a case. So this will be more clear with the help of an example. So here the same example which we were considering, now we will take two condition attributes, engine and size. Okay, so A is engine and size, and we have to see the dependability on A, on engine. Okay, so now B becomes engine over here. So A star will be nothing but all the equivalence classes. So here X1 will be equivalence class on engine, X2 will be equivalence classes on size, and X3 will be equivalence classes on color. How this is calculated, I have explained you in our previous lectures. Okay, now we will calculate B star. B star means all the indissolubility classes on B. Now B is engine, right? So in previous case, the A was engine and size together. Now, when we were calculating B star, we will be only taking engine. So only X1 will be considered. Okay. This equivalence class would be considered. Now, X2, what is X2? X2 is X2, X3 and X4. So X2, X3, X4, this is again another equivalence class only if engine is taken, because there are three domain values: propane, diesel and gasoline. So obviously there will be three indivisible equivalence classes: X1, X2 and X3. Here X1 is dominant on engine and size. So if you say engine and size for propane, obviously over here on propane is only one, so there will be only one member considering this. If you consider X2, X2 will be on diesel and medium. Okay, so diesel and medium, diesel and full. This is again a different combination. Diesel and medium. This is the same combination. So this X2 and X4 is repeated, right? That is why over here only X2 and X4 is another equivalence class and X3 is another equivalence class. I hope you are getting this because this is one set. Okay, the attributes are same, but here this is a different set. So if this is a different set, so the different equivalence class, different cluster has been formed. That's why X3 is different over here. Now another now domain value is gasoline. So if you can see here, gasoline compact here is same, gasoline compact here is same. So X5 and X8 can be grouped into one cluster or equivalence class. Whereas gasoline and medium is unique, gasoline is full is again unique. So we will have X6 and X7 separately as separate in equivalence class. I hope you have understood this. Then what we will do, we will calculate the positive region A of B. So A over here means lower approximation and B means the indivisible classes. So here we will do union of lower approximation. So you have to do the lower approximation of X1, X2 and X3 of these uh, equivalence classes, right? So what is lower approximation? If we consider X1, so X1 is this. So there is no ambiguity. Whenever there is propane, the decision is good only. So there is no ambiguity. So obviously you will put the lower approximation of X1 as it is, right? Now we will go to the another X2, which is this set. Okay, now why we have taken this as individual, this as separate, because this is all related to gasoline, right? Diesel, sorry. So if we take here, if diesel and medium is there, it is bad. Here also, if diesel and medium is there, it is bad. So this X2 and X4 becomes safe. So we can write X2 and X4 over here. Now what about X3? Now if X3 and full, so this is bad, but there is no ambiguity in any other column, which is, whenever there is diesel and full, there is no ambiguity that there is, apart from good, there is an option of bad. So even this becomes safe in terms of lower approximation. So it comes here because lower approximation says that when there is no ambiguity. Okay, hence this here X2, X4 and even X3 gets attached. Right now this is related to only engine, because see, B was only engine. That's why we are seeing only engine over here. So now next is gasoline. So third type of X3 would be totally on gasoline. So here we will take, this is one set, X5 and X8. So X5 and black, then it is good. Here it is X5 gasoline, not black, gasoline and compact. Here also gasoline and compact. But now it is an ambiguity here. When gasoline and compact is here, the decision is good. But here the decision is bad. Okay, so this will not come under lower approximation. Hence, if you observe 8 and 5, okay, 8 and 5 will not be separate. They will be attached to this X6 and X7. Now why X6 and X7? Because we are taking B only in terms of engine. So there should be no ambiguity. Even these things are different. But with respect to engine, the gasoline is the same on the left hand side. So if B is same, that you need not worry about it. You can put it all the attributes as it is. Clear? Now this is your positive region A with respect to B. Now how to calculate the dependency? We'll go back. The formula is cardinality of positive region divided upon cardinality of the total number of objects. So if you see here, what are the total the number of objects of positive region? 1, 2, 3, 4, 5, 6, 7, 8. So total 8 members in the positive region. So we wrote 8 over here. Okay. And what are the total members in U? They are also 8. Clear? So 8 divided by 8 is 1. So if it is 1, then we say that B is totally dependent on A, because right now we said that whenever it is 1, then B is totally dependent on A. So B is engine over here and A is engine and size. Likewise, see, you have to feed this in the algorithm in a for loop. where you need to consider every permutation and combination. So how many permutation and combinations? Since there are three uh, attributes. Okay, so one combination would be on engine and size, one would be on size and color, so two. Then one would be individually engine, three. One would be individually considered size, that is four, color five, and all three, that is six. So if there are three attributes, 2 to the power 3, that is 6, right? So you can consider this. Now we said that 2 to the power n minus 1. Why did I say n minus 1? Because obviously if you're going to take all these three attributes, definitely it is going to be considered as totally independent. So you can even discard that. But I uh, propose you that you better consider all the six combinations, even the entire set also. Okay, so likewise you have to find out the cardinality or the dependency of each and every attribute likewise, right? So after you calculate this, see, another combination is engine and size, and now B here is color. In previous case it was engine and size and B was engine. Now it is engine and size and B is color. So likewise now you calculate in a similar way, where now B would be color. Okay, so initially we calculated with engine. Now this is an example with color. Similarly, you can calculate with size. Similarly, you can calculate with engine and size, and so on. So now if you just have a look, okay, how it is calculated, it's easily given here. You can take a notebook and pen and start scribbling it, do an exhaustive search on the calculations. But ultimately 4/8, 0.5. That means color is uh, partially independent. What is the degree? 0.1. That means 50% it is dependent. Okay. Now finally, after you calculate each and every one, how to have a decision rule on this data set. This is very, very interesting, because this is the actual outcome on which you are working on your problem statement. You had inputs as your condition attributes, on your historical information, which was our basis. In our first lecture we had discussed what are the issues related to uncertainty, etc. So what is the solution? That you take the historical data. So now after the historical data, you understand that on these condition attributes you have these decision attributes, right? So after that you need to identify the decision rules for your problem statement, so that you can finalize your algorithm. So coming to this example, the decision attribute with domain values good and bad, right? Now this D star will be Y1 and Y2. So there will be two equivalent classes for D star, because D star is decision attributes. So I already told you that how many D star would be there. It will be depending upon the domain values. So for example, in engine, if engine is the attribute, suppose A is equal to engine, and engine has three domain values. So how many equivalent classes would be there? Three. Similarly, if A is equal to size, how many domain values are there? Compact, medium, and full. That means here also three domain values. So how many equivalence classes would be there? Three. Okay. Similarly, here black, gold, white, and red, even silver. So there are five domain values. So if you consider color, you will have five equivalence classes. So if you come to decision attributes, there are two domain values. So two equivalence classes, and we name them as Y1 and Y2 over here. Okay, so for Y1 it will be X1 because good, even X5 is good, even X6 is good, hence X1, X5 and X6. Similarly for bad it is X2, because here if you say it is bad, then X3, if you come here, this is also bad. If it is X4, then this is also bad. Then X7, here this is also bad, and X8, this is also bad. So this is Y2 is the decision attribute equivalence class where the value is bad. Okay, the car is in a bad condition if those condition attributes are considered. So DES, that is the disability relation, we already studied this. This is the smallest cluster, which is also known as, see, I'll go through that slide so you get refreshed. Of course, this explanation was given in the previous lectures, but where it has come from, okay, just to connect, see here, DES. So DES is the smallest divisible group of objects, which is also called as A elementary set. That means it is a equivalence class, the smallest cluster, okay, which we can represent. So indisability relation is a classification in general, and disability relation is cluster. Okay. And we have seen what is the difference between classification and cluster in our previous lectures when we had tried to identify the machine learning and data mining model in terms of predictive and descriptive approach. Okay, so now coming to this here. So D is D of Y1. Okay, that means when D is equal to good. Okay, and ds of d is y2, that means when d is equal to bad. So there will be two disability clusters. So now consider a is equal to engine. So what will be a star? A star is nothing but the indisability relation. So x1 is equal to x1, because if you consider engine propane domain value, there is only one attribute, one tuple related to x1. Then if you consider diesel, then you have 3. If you consider gasoline, then you have these many. Okay. Now where dsa of x1 engine is equal to propane, dsx2 where engine is equal to diesel, and dsx3 where engine is equal to gasoline. So this is how you are going to use the if then else in your whatever programming language, and as a decision rule to identify the conditions on which you can decide whether your selection of car is good or bad. So if we see here x1 intersection y1. So x1 is the equivalence class related to propane, and y1 is the decision where the car is good. So if you take the intersection, it is x1. Okay. And x1 is nothing but equal to the capital X1 itself. If you go back and see, capital X1 is equal to small x1 itself. Now since x2 intersection x1 y1 is 0, okay, and x3 intersection y1 is equal to x5 comma x6. So what we conclude, one rule we can have, T11, the disability relation of D with respect to y1. T13 is disability relation of D with respect to y1. Okay, so this is x3 and this relation is T13. And this is related to y1 where the car is good. So how actually after this mathematical logic you are going to represent in your programming languages T11 or T11 if engine is equal to propane. Why we are saying T11? Because it was on equivalence class X1 and equivalence class X1 on engine was on propane, X2 was on diesel and X3 was on gasoline. So similarly T11 is on propane, T12 is on diesel and T13 is on gasoline, right? So here since T12 is 0, so that's why that is not considered in our if then else. Okay, because now our entire analysis is on the good car. When the analysis will be on the bad car, then probably this would be 0, this would be x2 x3 x4, and this would be again x5, this would be x7 and x8. Okay, so that will be that year it will be y2 in terms of y1, because now we are deciding about the bad car. But in this particular case, now coming on to this T11, how you have to write, if engine is equal to propane, then D is equal to good. And T13 is if engine is equal to gasoline, then D is equal to good. Okay, so this will be only term for x5 and x6. Now as x1 intersection y1 is equal to x1, we already said this is equivalent to x1, and x1 intersection y1 is not equal to x3, because see here it is x5 and x6, but if you go back, x3 is actually x5 x6 x7 x8 x9 x10. Okay, so that means the intersection is not equal to x3. Okay, hence we can now say that T11 is deterministic and T13 is non-deterministic, because this condition is not equal to the equivalence class. And in other terms, you can say that whenever the engine is propane, the decision is deterministic. That means whenever the car engine is propane, your decision would be good, because it's not contradicting over here. But the moment we say that the engine car is gasoline, we can't predict. It may be good and it may be bad. So this is non-deterministic approach. So the moment we come to non-deterministic approach, the rough set classification goes into picture. So these are the rough classes, right? So we need to work now more on the T13 for later part using rough set theory. Okay, so basically where this is being used, it is most suited for the concurrent or parallel and distributed processing. So to implement it, you have for a see in today's world, internet and mobile applications, anywhere, anytime applications, pervasive, pervasive computing, ubiquitous computing, they all are using parallel and distributed processing at the back end. So this is a very much in demand. And for this rough set theory, Reducts, core, decision rules would play a major role, because in these scenarios, the data set is at times missing. It is unrealistic. It is uncertain. The imprecision is there. Okay. So to handle that uncertainty, and since the data set is increasing day by day, okay, its chances are very rare that it will decrease, and it's increasing on a very rapid speed. So probably rough set theory would be very efficient to even calculate the reducts to reduce the size, so that you will be able to access the decision rules faster. Okay, so we will stop here. These are some of the references which you can go through on rough set theory. The topic is totally mathematical, but I try to make it simple using this example, and then obviously convert it into coding, because you as a programmer, once you understand the model, mathematical model, then the next part is the design and the coding. So through this small example, I hope that it's clear to you how to calculate the deterministic and non-deterministic equivalence classes, and how to calculate the reducts and the core. Thank you very much for your patience listening. If you have any doubts, please mail me on ayeshabutalia@yahoo.co.in, or you can message me on the comment box or on the group. I would be very happy to solve your doubts. Thank you very much.